Hi, I'm Jason, and this is my artificial blood vessel report. So, for starters, we need to define what is a blood vessel. Well, a blood vessel is going to be a tube-like structure within the human body that is responsible for transporting blood. Now, there are two types of vessels. There are veins and arteries. The arteries will carry blood away from the heart and withstand much greater pressures as the heart is pumping it out. Veins carry blood back towards the heart and are at lower pressures. A simplified diagram can be seen here in the picture of just some arteries flowing through the leg. Now, the requirements for an artificial blood vessel, because we know what a natural one is. Well, an artificial one needs to be biocompatible. The materials that go in the human body need to be non-toxic and non-inflammatory. The artificial blood vessel needs to mimic the size, shape, and processes that is performed by the natural blood vessel, of course, so that way it can replace it safely. And the artificial needs to be able to withstand pressures equal to or larger than what a natural blood vessel can withstand. The artificial one also needs to be reasonably priced so that way it can be sold well and perform well as a company's product. Now, these are three biocompatible materials that will work for an artificial blood vessel. There's polyethylene tetraphthalate, or PET, polylactic acid, or PLA, and polycaprolactone, or PCl. Now, the research required for a SolidWorks simulation is important. In order to run the simulation, we need to know what the blood vessel volume flow rate is, the blood vessel radius, as well as the pressure inside the blood vessel. So for the simulations, we use the posterior tibial artery, which the diagram can be seen there. That artery flows down the length of the back of the calf. From research, the flow rate was found to be 26.5 milliliters per minute. The outer radius is 1.9 millimeters, and then that wall thickness is 0.556 millimeters. So the flow radius is 1.344 millimeters. The blood pressure is, for a normal blood pressure, is 120 over 80 millimeters of mercury. And the 120 is the systolic blood pressure, or when the heart is actually pumping the blood through the body, and the 80 is diastolic, when the blood is just sitting as the heart refills with blood. So for the flow simulations, we did use the higher pressure of 120 because that is when the blood is actually moving. Now, the SolidWorks model of the cross-section can be seen here. That is that full 3.8 millimeter diameter, or 1.9 radius, and that wall thickness of 0.556. And for the flow simulations, it'll be the tube in the middle that the blood is flowing through. So now we get to some setup designs. Now, these SolidWorks drawings here are not important for all of the specific details, but what is important is that they all are identical. 3 different lengths were chosen: 1 millimeter length, a 10 millimeter length, and a 100 millimeter length. And all of the cross sections are identical, the shapes and the functions are identical. The only thing that changes are the lengths, and that can be seen here in the drawings. Here is the 1 millimeter, here is the 10 millimeter, again, same cross section, just different length, and lastly, the 100 millimeter length. So then we get to, how can we run a simulation? We want to be able to run a flow simulation of the blood through the artificial blood vessel, as well as a static simulation of the forces on the blood vessel to make sure that our artificial one that we created is strong enough to stay in the body. So the material properties, we had to create custom materials in SolidWorks that aren't pre-programmed into it. PET is already programmed into it, however PLA and PCl needed to be added, and those values can be seen on the screen now. So once we input those values into SolidWorks and we get those custom materials in, now we can start the simulations. The first one was a flow simulation of the 1 millimeter length. The important value here is going to be that relative pressure maximum seen in the chart, which describes the maximum pressure felt on the inner side of that tube. Here's the static simulation using that pressure exerted on the inside, and we are now looking at the results of the stresses exerted on the tube. And so the stresses in the center of the tube are greater than on the outside edge of the tube, and that is going to be what we assess as the maximum hoop stress. Now, as long as the maximum hoop stress felt by the artificial blood vessel is less than the material's yield stress, the blood vessel will not burst and it will be a safe choice. The same process was done a second time for the 10 millimeter length. Same flow simulation, same table, different values. The relative pressure maximum is actually a little bit larger than for 1 millimeter. And a third time for, actually still on the second simulation here, just the static version of the 10 millimeter length, we can see that the stress felt on the inside of the tube is very similar to the 1 millimeter length. Now we do get to third, the 100 millimeter length, same flow simulation, same pressure table. However, the relative pressure maximum is much larger than in the previous two versions, and that pressure increase was put into the simulation for the 100 millimeter length, which is why the stress felt on the inside and the outside both increased, but it's the larger stress that we are concerned about. We want to make sure the maximum stress is below the yield stress for that material. So here's all the information summarized in these tables. In table 1, you get the pressures from the simulations, which didn't vary by material in the flow simulations, only by length, which is why only those 3 different values are input there. In the second table, we see the hoop stress that was created from the pressure input in the second static simulation. And then lastly, the table of values for the yield stress for each material. And as can be seen, those yield stresses are all much greater than the stresses that will actually be felt by the materials in the human body. So we know that PET, PLA, and PCl will all work as viable options for a blood vessel. And stress testing. We tested flow simulations at pressures at a flow rate that is 5 times larger than the normal volume flow rate. Previously, we used 26.5, and so the 5 times amount to stress test was 132.5 milliliters per minute. And even at a flow rate that is 5 times greater than normal, the pressures, the hoop stress pressures, did not exceed the yield strength of the material, and so they will still not burst at these greater amounts. So finally, the decision. What is best between PET, PLA, and PCl? Well, it will be PLA. It is the best material to use. It is similarly priced to PET. Although PET is the current standard artificial blood vessel material, PLA has some advantages over it. PCl is just simply too expensive to be a viable business option. PET only works for large diameters or blood vessels that are larger than 6 millimeters in diameter. PLA doesn't have that restriction. It can be used for small and large diameter blood vessels. It is also biodegradable, which means after it's been surgically installed in the body will simply heal, grow, and replace the PLA until the blood vessel has returned to its natural state, meaning no additional or extra surgeries are necessary. The body will just restore itself to normal. All of my references here for the document are included. Thank you so much for your time.